So, remember when Clojure saved you from the static void of Java gobbledygook? Yeah, I mean, many of us had that transformative experience, perhaps even life changing. But the real question is, can you save lives with Clojure? Should you put parentheses in your first aid kit? I don't know. Well, my name's Igor, this is Gerardo. Join us to find out. So, we'll start out with a little introduction of how we're going to go through the talk. We'll talk about our company, then we'll do a quick Sepsis 101, then we'll talk about how we try to solve it, then go to a little bit of technical dirty laundry, finish off with an inspirational message, a couple minutes for Q&A maybe, and then we're all off to lunch. So let's get going. We work for HCA. Now, the name probably is not familiar to most of you because we don't plaster it all over our hospitals, but in fact, we treat over 30 million patients every year at 178 hospitals across the US. That makes HCA the largest investor-owned hospital company in this country. Now, it is a hospital operations company, so we're not an IT company, which is not to say that we're Luddites. In fact, if you've been to a hospital recently, you probably get some idea of just how much technology permeates that space. I mean, we literally have thousands of people operating vendor hardware and software, from something as trivial as a blood pressure monitor that will wirelessly send your data to the electronic healthcare record system. But we also have something as sophisticated as robotic surgery systems. And yet what you have to remember about all of this technology is, while it starts out very exciting and new, over time it turns into legacy systems. So when was the last time you found faxes exciting? And yet, to this day, every year we send 120 million faxes to just one of our business partners. So how does data science fit into all of this mess? Well, you can think of a large company like HCA as something monolithic, but it's not. Think not aircraft carrier, think carrier group, where a fleet of business units works together towards a common goal. And so, yes, some of the business units will indeed do boring stuff, keep the lights on, keep the operation going, but some get to innovate and problem solve. And as problems go, sepsis is a big one. Now, sepsis is an overwhelming immune response to an infection. And it's responsible for 1.7 million cases in the United States and 1/3 of all hospital-related death. We all know how deadly heart disease are and cancer, but sepsis is number 11 killer in the US overall, number 9 in hospitals, number 3 in ICU, and number 1 in non-cardiac ICU. So what happens in that disease is that the body responds to infection by sending the immune system into overdrive. And so what starts out as a couple of out-of-bounds vitals very quickly turns to organ dysfunction and then system failure. Worse yet, it progresses really quickly. So the common metric in the industry is that 1 hour delay in treatment results in 4% increased chance of mortality. So early detection of sepsis is absolutely essential. But here's the dilemma. When your loved one is in the hospital, what do you expect from the caregivers? Well, of course, you want their full and undivided attention 24/7 throughout the stay. But it doesn't work that way, unfortunately. A clinician can't simultaneously be at the patient bedside while communicating with their relatives, while coordinating the care of the whole care team, while also dealing with all the administrivia, and at the same time sitting at the computer waiting for new labs, new reports to come in. And so this is where the difference in care setting becomes really important. 90% of all patients who are diagnosed with sepsis already have it when they arrive at the hospital. And yet it's the other 10% who are responsible for 25% of overall sepsis mortality. And if you look at the data, you can see that for that cohort, for those 10%, the treatment is not implemented as timely. They are more likely to develop organ dysfunction and they end up with higher mortality rate. Now, why does that happen? Well, think about a hospital visit. It usually starts with a flurry of activity. For example, emergency room, right? I walk in, I get triaged. If I'm not having a WebMD-induced case of hypochondria, they'll usually treat me, and then either send me on my way or will admit me to the hospital. But for patients who are already staying at the hospitals, those who have been admitted, we know what's wrong with them. We have diagnosed them. We figured out a treatment plan. And throughout their stay, generally speaking, they're recovering, they're getting better. The majority of the patients who are staying at the hospital will actually not develop sepsis throughout their stay. So we're faced with trying to find the needle in the haystack. What you're looking at here is a chart representing sepsis screening in one of our biggest hospitals. So what we do is screen every patient in the hospital twice a day. The two dark bands you're seeing is when most of the screenings happens. That's shift change. That's when nurses perform most of their documentation. But of course, it's not just then. You can see that some screening happens at other times as well. That's when the care team notices that something is wrong with the patient, and so they decide that they need to screen them right away. But with sepsis moving so quickly, remember, 4% increase in chance of mortality for every hour of delay. We're clearly not doing quite good enough. And the thing is, with nurses being so busy as they are, and the positive detection rate already being so low, more screening would not solve this problem. But perhaps computers could help us here, perhaps a bit of technology. Well, this is where we began our work. And the thing is, detecting septic shock, the late stage of sepsis, is really easy, but it's also too late. On the other hand, detecting early sepsis becomes a lot harder. It's a systemic infection. You don't get very clear idea what's going on. It's just small abnormalities across different organ systems. So, for quite a while, you could take 3 doctors, put them in a room, and ask them to come up with a definition of sepsis, and you would end up with 5 definitions. We, as an industry, struggle with this problem quite a bit. And so the way we started is we consulted with experts, we did our research, and we were able to come up with a definition that was acceptable to our physicians so that they could then implement care and they could trust our algorithm. Then we implemented the algorithm, and the graph on top shows generally what happened. So it's the same data as before, but here we're actually would be telling nurses when to go in and perform the screen. So we drastically reduced the number of screens. We went from 20,000 to about 700, and the positive detection rate would go up to 95%. That's great. The problem is this is a simulation. This is run over historical data. So what we needed to do, now that we had the algorithm, is to get it into production. And this is how SPOT was born, the Sepsis Prevention and Optimization of Therapy program. So we had the algorithm, and the main hurdles we had to overcome was, first of all, implementing it in real time on top of hospital data. And we had to deliver it to the caregivers in a timely fashion. Well, while working on that, we faced a number of technical and organizational challenges. This is what our electronic medical record system looks like. For those of you who feel that it doesn't follow the latest and greatest material design, this is actually an upgrade. It used to look like DOS recently. For all of you who can remember F-key galore, you know. And yet, you have to look past the pretty facade. The thing actually is underneath devilishly complicated because it has to integrate with every device, every system within the hospital. So it is, in fact, certain central nervous system of the hospital. And those things are not centralized. To avoid regional outages, they mostly run in the hospitals or hospital regions. That means that to integrate externally, they have to send something called HL7. This beauty. An ancient format for transferring clinical, financial, administrative data. It may look pipe delimited to you. It's not. Characters 4 through 8 will define how each particular message is delimited. It has a type system that can completely change the meaning of the segments. And if you're really having a bad day, you can actually embed PDF or Word documents in there. But, as I mentioned earlier, because of the decentralized model, hospitals also have an unfortunate degree of control over the content of these messages. So that means that we had to basically parse 180 dialects of HL7. So this is how the system worked. Now, I'm avoiding some details about metric collection, reporting, and more obscure business logic, but generally the application was built in Clojure, except for the Elixir UI. So on the high level, the HL7 messages come in from the hospital, they get aggregated, and they get put on Kafka topic. That's where we take over. The extract and transform service gathers the clinically relevant information, and then takes a subset of it and sends it to the detection service that cleverly uses Kafka compacted topics to build patient snapshots that are then processed by the algorithm to generate the detection signal. Now the UI is deployed in these rooms. This is monitor tech rooms. This is the place in the hospitals that looks like mission control center, and that's where we monitor high acuity patients 24/7. The arrow points to the spot screen there. So let's zoom in a little bit. So this is the application UI. This is where the monitor technicians actually receive the spot signal, and also this is the application that sepsis coordinators in the hospital using to manage their workflow. And to that workflow, the way it works is we get data from the hospital. If we get a positive detection, the spot signal is sent to the monitor techs. Monitor techs have 5 minutes to respond to the signal in application and figure out which nurse is responsible for the patient and contact that nurse. Now nurses are extremely busy. Not only they're busy, they're usually not very interruptible as well. So if they get a signal and they have to run to another wing, they'll probably finish whatever they're doing with the current patient. So nurses have 60 minutes to respond to the alert and perform the sepsis screen. Now, if they don't perform the sepsis screen, then it gets escalated up the chain of command to make sure that the screening is performed. But if the screening is positive, they will start implementing care right then. We will get the results of the screening regardless in the application, and if it was indeed a positive detection, we would then send it to the list for the care coordinator to follow up. Now you may ask, why do we do all of this sepsis screening? Why not just say, hey, go implement care on this patient? The thing is, we will always have less clinical context than the actual caregiver at the bedside. So who do you think looks like a sepsis patient in general? It's a pregnant mother who is about to deliver a child because all of her internal systems are out of whack at this time. And so interaction with the patient and clinical judgment are essential to the system working. This is why this is not a diagnostic tool. This is a clinical decision support tool. Now, all of this sounds very exciting, but how much of it is vaporware? Well, as of October this year, we're deployed at 165 hospitals across HCA. And I think more impressively is the fact that we were able to get to 165 hospitals in 6 months. Now, if you think about a hospital, every hospital is like a little kingdom. I mean, they have CFO, CEO, CTO, they have patients that they're responsible for, they have IT infrastructure, thousands of employees perhaps. I mean, a mid-sized business. That's why these implementations sometimes can take years. And yet it's a testament to the reliability and quality of the product, the strength of our team and our partners from the clinical excellence team, that we were able to build trust with hospital operators and deploy Spot in record time.
And it works. Let's take a look at some data from one of our larger hospitals over the last 2 years. Here we see severe sepsis mortality juxtaposed against the proportion of severe sepsis patients receiving timely treatment. Since Spot launched, we've seen a dramatic increase in the percentage of severe sepsis patients receiving timely treatment, and we've seen an even more dramatic and more important decrease in severe sepsis mortality. So much so that this is the lowest this figure has ever been recorded at this facility. And behind these numbers are real human stories. Let's take a look at a couple. Here we have an elderly patient admitted with shortness of breath and comorbid heart failure and COPD. 2 days after admission, spot alerts. The bedside nurse goes, assesses, confirms sepsis, and initiates a more aggressive treatment protocol. Because we're able to identify this early and enact treatment early, we were able to avoid a costly trip to the ICU. The patient was able to remain on the general medical surgical floor. Here we have another elderly patient admitted post-fall with comorbid hypertension, hepatitis C, and a urinary tract infection. For 16 days, this patient's immune system fought this infection until it eventually spiraled out of control, which is when spot alerted. Again, the nurse confirmed sepsis. In this case, the patient did require a trip to the ICU, but after 4 days, he returned to the medical surgical floor, and we were able to avoid a more negative outcome. So what have we learned on this journey? Let's take a look at some of our technical highlights. When we first started Spot, this was at the height of the big data craze. Spark was hot, everyone was using it, and we thought we'd jump on the bandwagon. But from the outset, it just kind of felt a little bit off. As best we tried, it still sort of ran a little bit slow, and debugging it was unintuitive, and it just didn't feel right. And so we did what any good Clojurist would do, and we took a trip back to the hammock and thought about our problem more deeply and what we actually wanted to accomplish. And we realized we just wanted to apply a function to every message on a Kafka topic. Now, that sounds a whole lot like Clojure map. In fact, it's not rocket surgery. And so we built an abstraction we call Kmap, which takes in a collection of Kafka input topics and takes a batch of messages from those topics and applies a function to each one of those messages in parallel using core async. Now, this function returns a vector of vectors, where each item vector is a tuple from output topic to some sort of transformation of the message. Today, we're happy to open source Kmap and release it back to the community. We hope you all find value and enjoy using it. Another one of our technical highlights had to do with Datomic. As Igor mentioned, Spot uses Datomic to store data, and we had a wonderful time using Datomic. Code data locality meant writing our services was intuitive and straightforward. In-memory databases made writing test case scenarios easy, and we were able to write realistic ones. And as best as we tried to come up with the perfect scheme at the outset, we inevitably were forced to modify it somewhat after we went to production. Datomic made doing a schema modification in production quite seamless. But Datomic wasn't without its few challenges. In particular, one of Datomic's biggest selling points is its immutability. But immutability is a double-edged sword, especially when you have 165 hospitals generating a lot of data 24 hours a day. We realized we needed a way to hot swap databases in production. So we came up with a procedure we call just-in-time rollover. When our initial Datomic databases reaches capacity, we create a new Datomic database to temporarily halt consumption from our Kafka topics. We then copy application state, so these are patients actively being worked on by clinicians, to the new Datomic database. Once that copy completes, we start consuming from Kafka again, but not before inserting another component at the head of our pipeline. And this component will read every message coming through on Kafka and look up that patient in the previous database. And if that patient had not yet been discharged from the hospital, we'll copy that patient's data in the old Datomic database, in addition to whatever new data came through in that message, over to the new Datomic database. And that is the just-in-time rollover. Now, we do incur a little bit of downtime in this procedure. And as a clinical application, we want to minimize downtime. We want to maximize availability as much as possible. So we took this a step further and sharded our database evenly with roughly 30 to 40 hospitals per shard. This allowed us to reduce the need to roll over to about roughly once a quarter, which is a lot more palatable. So another challenge we faced with Datomic is a curious side effect of running Datomic inside OpenShift, Kubernetes if you're not familiar with it, Red Hat's flavor. So say, for example, we get an email from a clinician asking why so-and-so patient alerted at this time, or what sort of other data points were available in this patient's context or whatnot. This requires a query against the production database. That's fine. We know how to query Datomic. You stand up a peer, and then you connect to the transactor, except your transactor lives in OpenShift, and it lives behind a software-defined network. which means I can't easily stand up here on my laptop and talk to Datomic. And so our first idea was, okay, let's just use the GUI that OpenShift exposes in the browser. Well, it would be very kind of me to say that the formatting in this GUI terminal was atrocious. And the terminal is also prone to closing suddenly on you, in particular just after you initiated a query. So our developers were getting really angry, and we realized, all right, this isn't going to work. Luckily, around the same time, one of our colleagues, Christoph Grand, debuted unREPL at last year's Conj during an unsession. I had an idea, what if we use unREPL as the basis for a Jupyter notebook? Now, unREPL has this really nice property that it exposes a REPL protocol that allows you to allows you to ship dependencies from, say, a Maven repo to a remote socket REPL. And so we did just that. We were able to put together a Jupyter notebook kernel called iClojure, based on the unREPL protocol, that allows us to stand up a Jupyter notebook locally and connect to an OpenShift socket REPL via an SSH tunnel. And from there, we can query Datomic databases to our heart's content, and this is what we do day to day in Spot today to answer customer support emails. And we're happy to open source iClojure and contribute this back to the community, and we hope you all enjoy. Let's go through a quick demo. You start off by standing up your Jupyter Lab environment. So we started off with Jupyter Notebook, then we progressed to the newer Jupyter Lab. You select your kernel, in this case, iClojure. And from there, you can connect to a local JVM. Now, it takes a minute, knowing Clojure startup times. But once it's connected, you can execute arbitrary computation. From there, you stand up your SSH tunnel. In our case, for OpenShift, you use port forwarding, which forwards the exposed socket REPL port to your laptop at a port of your choosing. Forgot to start the video. There you go. Once that's completed, you are then able to connect in the Jupyter Notebook, as we'll see here. And so once this connects, you'll be able to execute arbitrary computation on the remote socket REPL. So let's say I'm in the notebook and I have some data, and I want to do some sort of computation over it. I'm in the flow. May even do some transducer silliness. So I pull in Christoph's X-forms, and it's great. Works fine. But say I want to compute something a little fancier, say a standard deviation. I don't really feel like re-implementing, so I'm going to load KXIstats. Except I did not think of adding KXIstats to my dependencies at the outset. So what do you generally do here? You go to your Line-Again project CLJ, you add in KXIstats, you kill your nREPL, you start up another REPL, and you start over again. Or maybe if you're using some sort of Kubernetes environment, you have to redeploy a pod or something. But not with iClojure. With iClojure, you simply add the KXIstats Maven repo to your class path, and then require it. And unREPL will take care of pulling down those dependencies and shipping it to your remote socket REPL. And so here I'm doing the require, and it's actually putting the dependency on the wire. And once that's done, that's it. I can continue my workflow without having to be interrupted and have to redeploy pods. Some of our more experimental work with iClojure has to do with lazy loading of data structures based upon mouse-driven actions. So here we have infinite sequences that we're lazily loading with clicks. Yeah, we're pretty excited about it too. And now with Spot deployed at all of our hospitals, we are focusing on how can we generalize the Kafka-based architecture we built to a variety of different enterprise data science use cases. And all of this technology is great and exciting, but let's not forget what this is really all about. A few months ago, one of our larger hospitals, a mother had just given birth to a healthy baby girl. Shortly thereafter, Spot alerts. The care team goes and assesses the patient, and they don't notice anything too unremarkable, except for a bit of low blood pressure, which they were able to treat with fluids. As expected, she had somewhat of a soft, saggy abdomen, but this is par for the course given a C-section. 3 hours later, Spot alerts again. This time the care team is quite a bit more concerned. They order blood work. When the results come back, they see that her hematocrit and hemoglobin levels had dropped precipitously. She was bleeding. She's rushed back to the OR where the surgeon discovers an abdominal arterial bleed. She lost nearly 4 pints of blood. Sorry, 4 liters of blood. But she lived. Thanks to Spot repeatedly drawing the attention of the care team, a mother was able to leave the hospital with a newborn daughter. And if this sounds like a mission you can get behind, please join Igor and myself for lunch, and we'd be happy to tell you a little bit more about our day-to-day. Thanks for stopping by.